Swayam Prabha. Digital India. Educated India.
In the previous lecture, we initiated a discussion on the variational approach to the derivation of the Young-Laplace equation. The problem setup, the schematic of the problem setup is shown on your screen. We considered a sessile drop that's sitting on a flat, smooth flat interface, fluid flat solid surface, and it's in a partial wetting regime, and we're having a contact angle of theta e, that is the equilibrium contact angle at the contact line. We also have considered gravity into account, so this is different from some of the earlier lectures where we had ignored gravity. We wrote down an expression for the total energy. This includes the surface energy, then we have the gravitational potential energy, and finally we also imposed a volume constraint. So the total energy functional that we want to minimize, the auxiliary function, is basically now a combination of the surface energy, the gravitational potential energy, and the volume constraint imposed using the method of Lagrange multipliers. What we then did was to write down an expression for each of these quantities in an integral form. We've restricted the analysis to 2 dimensions only to keep the analysis simple, to reduce notational effort. And the final expression that we have for this energy functional J, this auxiliary function J, it's a function of 2 variables, the height h and its derivative hx. Here hx indicates the derivative of h with respect to x. We defined the quantity in the integral with another function called capital F. And so what we now want to do is, we want to do an energy minimization, or we want to use a variational approach on this quantity that we have, on this integral that we have. Let us proceed with the analysis. But before we proceed with the analysis, let's understand why do we have a variation at all. Let's consider a flat solid. On the solid is sitting an interface, a drop solid interface as follows. Now, we also said that this integral is going from a to b. So, my a is, let's say, on one side and b is on the other side. Now, you could have variations to this functional if there are variations to the interface position. Let's say the interface is basically perturbed, or I look at a variation of this interface position like this. Okay. So my blue curve that I'm showing here is my h naught of x, and therefore we can write down the variation and the variation of this height from the h naught of x. We'll call this as epsilon eta of x. Okay. Now it's also important to understand that this variation can also induce a variation in the position. So let me make some room here for writing down showing the variation. So the variation in position, let's say, is you have the original position A and B. You could also have variation in the position. This variation in the position, let's call it as delta A, and the variation of the position B is delta B. Okay. It's just a coincidence that both these variations appear positive, but the sign does not matter. It's just an arbitrary interface shape that I have drawn. Okay. Let's start by writing down the variation of this functional J. Variation in functional J is given by delta J. This could happen because of variations in this quantity, delta of A to B, f of h hx dx. So now it's important to understand this integral a bit more, this expression a little more carefully. So the variation in j could occur because of variations in f, and variations in f in turn occur because of variations in the height and its derivative. You could also have variations in the position, which means it could also because of variations in the contact line positions. So the variation need not come and meet exactly at the original position, but could also be at slightly different positions. So that variation in the contact line position is shown as delta sub a, delta b, and delta a, where those are along the solid surface. Okay. So now we will define this quantity h of x as h naught of x plus a variation in h, and this variation of h can simply be defined as epsilon eta of x, where epsilon is very, very small and eta of x is an arbitrary function. Alright, so this is so far we're following the procedure that we had followed for the in the case of static meniscus derivation, and also in the variational approach, introductory variational approach lecture that I had given. Okay, so here h naught of x is the equilibrium shape that we seek, and eta of x is an arbitrary variation about h naught of x. Okay, so there are several ways to do this. We can one of the ways is to substitute this variation into the expression and do a Taylor series expansion. I will take a slightly more direct approach. So variation in delta j is nothing but, let me write this down for completeness again. We have a to b f of h hx dx, right? So this could be variation in the positions. So if I just think of them as two separate functions, I can directly integrate them, and I have for a fixed f, I could have variations in the position. This is f at b minus f at a. That's the first one. So I'm just think of it like I'm using a product rule here. Integral of two quantities f and dx. Now dx would just be b minus a, but now we have variations as well. So the variations of b and a come in. That's the contact line positions. And then I have variations in the function f itself. The variations in function f, it's a function of two variables. Therefore, I have variation with respect to, remember these are variations, the variations come about because epsilon is not 0 right now. Okay, so we have del h, del f by del h, del h by del epsilon times d epsilon plus the variation with respect to hx, del hx by del epsilon times d epsilon times dx. Okay, so the first two terms are variations because of delta dA and variations of the position, arise from variations in delta A and delta B of the contact line. Okay, that's the first observation. The second term in the second integral, I'll highlight it for your benefit. The second term in the second integral is this quantity here, can be further simplified using partial integration. Can be further simplified by partial integration. So what do I have here? The second term in second integral is integral del f by del hx by del epsilon d epsilon dx. This is what we have, right? This is from A to B, and this quantity is nothing but del f by del hx times del h by del x. Because integral with respect to x, I can directly do an integration. Hx becomes h, and I have d epsilon. This is from A to B minus integral from A to B d by dx of del f by del hx times del h by del x d epsilon dx. This is what we have. Therefore, delta j, that's a variation in the functional j. Now putting together, we get del b f of b minus del a f of a plus, now I can basically take the first term in this quantity here. Now if you look at this quantity, first term in this quantity, we have this quantity here is, I made a small error here somewhere. This should be derivative with respect to epsilon, sorry. This quantity here is nothing but delta h, right? So I have del f by del hx delta h at A and B, and minus, or rather I can combine this term here with the last term here. That's what I'm highlighting, these two terms. I have plus del f by del h minus d by dx of del f by del hx delta h dx. This is going from A to B again. So note that this expression here in this integral, this is nothing but the Euler Lagrange equation for capital F. Okay, right? So let's now understand these variations. What about these variations at the contact line positions? Okay, what about them? Now you can write down that the variations of the contact line positions, let's call them as delta A and delta B, that's what we have. These quantities are not independent of the height. Height variations, right? So what do I mean? For example, if you take a contact line here, if I were to zoom in to the region near the contact line. Let's say this is the original contact line, this is A, and there is a variation in the height. Either if there is a variation in the height, let's say because of some variation in the height, this straight away impacts this height variation will also lead to a variation in the position. If there was no height variation going all the way to the contact line, then there is no reason to expect that there will be a variation in the contact line position. So now you basically understand that this variation in height essentially comes about, variation in height also has an effect on the variation in the contact line position. So these are interrelated as follows. Variation in height about B is just the variation at B times delta B. Okay. So we could also obtain this result by just doing a Taylor series expansion and keeping only the first linear terms. So we now have the variation in the energy functional will be variation in the let's write this down, delta B, that's what we have here. Now I want to combine these terms here. I want to combine these terms because these terms are the third term in this integral, in this functional expression that have variation functional. They are evaluated at A and B. So I'm going to have delta HB and delta HA terms, and that's exactly what I'm going to combine now. So I have F at B minus the variation from the boundary term. This term that I've just written down comes about from the when we did the partial integration. These are two terms. Now we have to write down finally the expression that we had in the final term, that is the Euler-Lagrange equation. This delta H, remember, is a function of x. This whole variation will set it to 0, right? So that's what we have. Now, since delta J has to vanish for arbitrary variations, the delta A, delta B and delta H, since it has to vanish for arbitrary variations in these quantities, what do we now require? We require each of the quantities in the parenthesis to vanish. Terms in each parenthesis to vanish independently. So in other words, we have FB minus del F by del HX of HX at B 0, FA minus partial derivative of F with respect to HX times HX at A 0, and finally we have del F by del H minus d by dx of del F by del HX should also be identically 0. So we have three expressions that we've got, right? So these two are boundary terms, and we will soon see that these boundary terms will help us get the Young's equation at the contact line, and this is the Euler-Lagrange equations. And this, the Euler-Lagrange equation, will help us get the Young-Laplace equation, which kind of helps us connect the Laplace's law and the Young's law together in one. They can be combined with one bigger law of wetting, basic law of wetting that we can derive. Okay, so these are the three expressions that we have. Now let's make use of the expression for the quantity f. Okay, recall that f, this quantity f, is a function of h and hx in itself. And what is this here? Which is gamma times 1 plus hx square plus gamma SL minus gamma solid. Then I have half rho g h square minus lambda h. This is the expression for gamma. Let's calculate some of these quantities. Del f by del h is nothing but rho g h minus lambda. Del f by del hx will be gamma times 1 by 2 hx. That is nothing but gamma times hx by 1 plus hx square. It's important to not make the mistake that this is a derivative with respect to x. It is not. It is a derivative with respect to hx. So hx is the variable. So you should not further differentiate it using the chain rule. Okay. And finally, we need, in the Euler-Lagrange equation, we need the x derivative of this quantity, del f by del x, del h, d by dx of del f by del hx. And we have 1 plus hx square. Let me quickly do this. I have hx and if we simplify this, we are simply going to get gamma times hxx by 1 plus hx square whole power 3 by 2. This is what we have so far, right? So if you look at the last term, the Euler-Lagrange equation, let's label these equations rather. Let's call this equation as equation 1, equation 2, equation 3. Okay. So we now have, from the equation 3, we have del f by del h. That is, del f by del h is nothing but rho g h minus lambda minus d by dx of del f by del x. So that's minus gamma hxx by 1 plus hx square whole power 3 by 2. This is equal to 0. Okay. This is an important result that we've got. We have not, we could have also done one more thing. We could have treated lambda to be another variable and taken the derivative with respect to lambda. I haven't done this to keep the analysis simple, but we could also do that as well. But we will compare this expression that we have got now, that I have put this in the box. We'll compare this expression with the expression for the normal stress balance, the jump condition for pressure across an interface, and you'll see that this lambda will turn out to be the pressure jump, or it will turn out to be the a difference in the pressure, and I'll explain what that means, but we'll hold on to this expression for later analysis. Okay, so we'll now look at, let's say, at the contact line. That's, let's say, from 2. This 2 relates the relationship between the value of the function at a to its derivatives at a. So what we have now is fa minus del f by del hx times hx. This is what we have, right? So if you substitute this, what do I have here? Gamma 1 plus hx square plus half rho g h square minus lambda of h of a. This is the expression for the function at a minus gamma hx square by 1 plus hx square. All of this at a is equal to 0. We have to evaluate this at a. Okay. Now we'll simplify this a little bit. We can multiply throughout by square root of 1 plus hx square, and what do I have as gamma 1 plus hx square plus gamma SL minus gamma S of 1 plus hx square plus half rho g h a square minus lambda h, this multiplied by 1 plus hx square, and finally I have gamma hx square is 0. Okay. Now if you see the schematic that I have drawn here, if you approach the point A, then the height goes to 0. The height, remember, is this h, right? As you approach the contact line, the height basically goes to 0, and therefore we can now say at a, h of a goes to 0, and this essentially means that these terms go to 0, and I therefore have gamma 1 plus hx square gamma SL minus gamma S of 1 plus hx square in the square root minus gamma hx square is 0, right? We can cancel out the hx square terms in the first term and the last term. I therefore have gamma plus gamma SL minus gamma 0. This is what I have. Now let's look at what this actually means. For example, if I have a contact angle of theta e, as I approach the interface, let's say this is dx and this is dh, then I can write down an expression for this. The angle, the tan of theta e is nothing but dh by dx, right? And therefore square root of 1 plus hx square is nothing but secant of theta e. If I substitute this, I have gamma plus gamma SL minus gamma S of secant of theta e is 0, or I simply have gamma cos theta e. This is one of the variations of the Young's law, or another way to write the Young's law is the cosine of the angle at the contact angle will give me the relationship between the surface energies. Young's law. Okay. Now note that the gravity term drops out. Gravity term drops out from this boundary condition. This suggests that this law should be applied only very close to the contact line. Okay. This is not surprising, since this relation is valid very close to the contact line. In most cases, this relationship that we have here serves as a boundary condition at the wall. Okay, meaning the slope of the interface as it approaches the wall is given by this Young's law gives us that relationship, because it tells us, it imposes an angle condition. The slope of the interface is directly related to the angle, or rather in fact the tan of the angle. So we have got the Young's law. We can do the same thing on the other side as well, for the other boundary condition, that is equation 1, but I will leave you to try and do this yourself. And therefore now what do I have now is we basically got the Young's law. Okay, what about the equation that I put in a box and I left it there? This equation that I'm just highlighting, let's say with the equation, I'll call it star. Okay, what is this equation? Okay, let's understand this equation a little better again. Let's revisit this equation. What do we have in this equation? We have rho gh minus lambda minus gamma times hxx by 1 plus hx square whole power 3 by 2. This was 0, right? Now let's recall the jump condition, or rather the normal stress jump condition for a static interface. Let's recall this condition. What did we have here? If we consider an arbitrary interface like this, where we have the lower side, let's call it as minus, and the upper side we call it as plus, then the condition was that the pressure on the upper side minus the pressure on the lower side at the interface, meaning I'm just considering 2 points across the interface, this would be minus gamma times del dot n, where n is the normal vector, right? Now this quantity del dot n is also the curvature. Okay, now we had calculated the value of this quantity del dot n. We have calculated this both in previous lectures in this expression of variational calculus that we're doing. We had also written down the expression for the normal vector n in 3 dimensions, but you can just ignore the variations of h with respect to y and write down the calculate del dot n, and this will turn out to be minus hxx by 1 plus hx square whole power 3 by 2. Okay, now let's understand what is p plus and p minus. Okay, let's apply to the problem that is at hand. So we have a droplet like this. We'll say that the pressure above is P infinity. Okay, so we are interested in the pressure above, just the little above and little below. This is, remember, this is plus and minus. Okay, and we'll also say that the height is h. So at the bottom of the plate, at the bottom, let's say the pressure is P naught. Okay, so as you go from the bottom of the plate and as you go up, the pressure at just below the interface, as you go from the bottom, will obviously reduce because of you're going up in height. So it will decrease from P naught because of hydrostatic reasons. So that is because of gravity. That's just the variation of pressure with height. That's a hydrostatic condition. And the pressure at the top, we'll just call it as P infinity, right? And therefore I now have P plus, that is P infinity, minus P minus. What is P minus here? P naught plus rho gh essentially becomes minus gamma times curvature, right? Or I can now write down P infinity minus P naught is rho gh plus gamma times curvature, or I can simply have this is delta, we'll call this as delta P is rho gh plus gamma times curvature. So this is a very, very important result. Using curvature, expression for this curvature is minus hxx by 1 plus hx square whole power 3 by 2. We now have delta P will be rho gh minus gamma times hxx by 1 plus hx square whole power 3 by 2. So these two expressions, they are the same equation written in different forms. They have substituted the expression for curvature. This is a very, very important result. This is called the Young-Laplace equation, because if you notice here, we've done two things here. We've got a variation of pressure because of gravity. So in the absence of surface tension, if surface tension was identically zero, then the pressure the variation of pressure is only because of gravity. That's what this effectively reduces to. If there was no gravity at the interface, so if there was no gravity in the problem, then the variation of the pressure across the interface, delta P, will simply be the surface tension times curvature. Now note that if there was no gravity, the pressure P naught inside the droplet would be uniform. So we have a uniform pressure inside the droplet, and this uniform pressure will differ from the pressure outside. So that's what this relationship tells me. And finally, we have in 3D, the same result carries over, but the only difference is now I have to write down, there may be two curvatures, so I have to write down the mean curvature plus rho gh. That's the expression in 3D. Okay. So what we have done in this lecture is we have considered the case of a droplet sitting on a surface, and we have considered the variation of the height. If there are small variations in the height, this will lead to a variations in the energy functional. And this variation in the energy functional, we minimized it. We set the variation to 0, and in the process, we got boundary terms at the two contact lines that we have in the problem at A and B, and we also got the Euler-Lagrange equation. Now substituting the expression of the function in both these boundary terms, we had labeled these relations as 1, 2, 3. We basically 1 and 2 yield the Young's law, and the third equation gives us the Euler-Lagrange equation, essentially gives us the Young-Laplace equation. This Young-Laplace equation is a very, very powerful result because it tells us for a static problem how all the variation in the pressure is connected to the variations because of gravity and the curvature. This technique can be directly extended to the case of a pendant drop. For example, all I have to do is change the direction of the gravity, and instead of a drop, if I have a drop like this is referred to as a sessile drop, where gravity is downwards, and this is a drop sitting on a plate like this. You could also have a situation where I have gravity downwards, but then you could have a droplet. If you have a droplet like this, this becomes a pendant drop. Now this pendant drop is a very important, we use again if I want to shape of this pendant drop, I use exactly the same Young-Laplace equation. The only difference is that the value of gravity will have to change. We have to change the sign, But it becomes very important because the solution of this equation becomes very important because if I look at this equation, everything is practically known. Once I know the height of the droplet, I know the value of gravity and the density. I can determine the second term. I can determine I can measure the first term. The only thing that is unknown in a typical problem like this in a surface tension measurement is the value of gamma. So I can actually I can reduce it to a one parameter family of solutions where gamma is the only variable. So if I were to do an experiment, I would basically determine the shape of the drop, capture it typically with a camera, and then fit the various solutions that are possible. I'll do a fit of this solution of the Young-Laplace equation to the shape that I have in the experiment, where the only unknown parameter is gamma. So I can actually determine the value of surface tension in that way. So this is one of the most common ways of measuring surface tension in a laboratory. So anyway, so I think we have come to the end of this lecture. We have looked at the shape of a droplet in the presence of gravity. And in the next lecture, we will just extend this a little bit and look at the shape of the size of a puddle as well. And that will conclude the discussion on droplets. I would like to briefly discuss the various techniques that are commonly in vogue for measuring surface tension as well. But we will do that in the end of the discussion on capillary statics. I'll see you around in the next couple of lectures. Thank you.